Hello, here's part B of the 2008 PAT. So we had the maths questions in part A. We've now got 10 multiple choice physics questions. So I'll do those in this one and then do the written ones in a subsequent video. We still can't use calculators in any of this, but I don't think that's going to be much of an issue. Right, question 13. The symmetric seesaw is 3 meters long from end to end. If a boy of mass 20 kilograms sits on one end, how far away from him should a girl of mass 30 kilograms sit to balance? So we've got this. We've got 20 kilograms at one end. So that's going to be at 1.5 meters. So we're going to want to have the 30 kilograms just 1 meter away in order to balance that with our moments. Or 1 meter away from the pivot, because weirdly it's got how far away from him. So you need to be careful with the wording of some of these questions. That we got 2.5 meters going for D. All right, question 14. When nuclear fission occurs in a commercial nuclear reactor, the mass of the products compared with the mass of the reactants is, well, it's got to decrease because that's where we're getting the energy release from. That difference is the mass defect, which is the energy release, so it's going to be B. The visible universe contains about 400 billion galaxies, so 1 billion is 10 to the 9. Our galaxy contains 450 billion stars. The mass of our sun is that. NASA estimates that dark matter outmasses stars 20 to 1. Use this data to estimate the total mass of the visible universe. Right, so our visible part, our 1 in this is going to be 400 billion, so it's 400 times 10 to the 9. That's the number of galaxies. Then the number of stars in each galaxy, roughly speaking. Then the mass of each star, so that's 1. So we're going to need to multiply that by 21 to get the 20 plus the 1 in the ratio. So putting all of that together, so how many things have we got here? So that 4 times that 25 gives us 100. So that's 2 10s, 3 4 13 14 23 53. So 4 that's 42, so 4.2 times 10 to the 54 kilograms is what we've got, which is D. Right, moving on. These are going very quickly. The question 16, the solar eclipse can only occur when the moon's phase is right. So this needs a little bit of knowledge of what's going on. So, well, to have a solar eclipse, you need to have sun, moon, earth. That's what we need to have going on. So the moon has got to be in the middle, which means typically we wouldn't be able to see it. You know, we get a full moon if it's on the other side because the light is all reflecting back at us. So we need it in the middle, which means we're going to have a new moon. So that's going to be A. Right, that's 4 of them done. Next page. When an ideal gas is heated in a container of fixed volume, then what is going to happen with, so we're looking at pressure and density. So we want the pressure to go up, but the density is going to stay the same because we haven't changed the mass or the volume. So which one of those? Pressure, here we go. So C. 18. A physics lecture theatre is situated 3 meters east and 4 meters above reception. Calculate the minimum energy a 60 kilogram receptionist would have to expend to reach a lecture theatre. Right, well, if they've got a really slippery floor, then we don't care about that. They've just got to do an MGH on that. So we're going to have 600 times 4 is B. Question 19. A 3.6 volt mobile phone battery can produce 0.7 amps of current for 1 hour. Okay. This can be charged using a square solar panel of that size, efficiency 10% with that incident solar power. What time is needed to charge the battery? Right, so the energy that we have used is, so the battery can do 3.6 times 0.7. That's our power. That's our joules per second. So we need to multiply that by the number of seconds. So that's the energy. Actually, the answers are in hours. So let's leave that out. So that's just going to be, so that is our power that we've got there in our joules per second, that number of watts. So we need, assuming efficiency of 10%, right? So we've got a quarter there. So we've got a quarter squared. That is our area of the solar panel. So we need to multiply that by the incident power. So that is multiplied by 10 to the 3. We need to multiply by our 10% efficiency. And then if we keep everything in hours, then yeah, we can just say that's multiplied by t, and we need that to be equal to the same thing. So what have we got here? That's going to cancel with one of those. So we've got 100 over 16 all in all. So yeah, that's our energy in multiplied by t. That was our energy out multiplied by t. And these things need to be the same. That t is just 1, so that's why we can ignore all the 3,600, because we're saying we've got that wattage multiplied by that time. So now we've got that wattage multiplied by that time, and these two things have to be the same. That t is just 1 if we stay in units of hours. So yeah, I can convince myself that that's okay. So that t then is going to be 3.6 times 0.7 times 16 divided by 100. Okay, so what's going to be the best way of navigating our way through that as an answer, if we can't use a calculator? So this 3.6 times 0.7, so we've got 2.1 plus 0.42, so that's 2.52 more or less divided by 6, give or take. So that's gonna, well, it's gonna be divided by a little more than that. So that's going to come out, because yeah, 16 over 100. If it was 16 and a couple of thirds, then we would have got divided by 6. So it's dividing it by a little bit more than that. But either way, that's going to come out as C. Yeah, because it's the only thing that's close to being 0.4. It's about 24 over 6, that sort of order. Anyway, yeah, that was stepping it up a bit on that one. So question 20. Light dependent resistor is connected across an ideal 12-volt source and placed in the open in the middle of a desert. When is the power dissipated in the resistor highest? Right, so resistance decreases as light increases. The power is V squared over R, so we want a low R, which means we want a high light, which means we're going to want it to be, what are the options? Well, noon is going to be more than midnight, dawn, or mid-morning. So yeah, so I'm happy with that one. 21, I think we just got 2 to go. So question 21, a bullet with a mass of 10 grams fired at that velocity into a cubical tank of water, 2 meters on each side, brought to halt by friction. Right, so we're putting some energy in, and calculate the temperature rise of the water. So the energy in is going to be our half mv squared. So that is a half times 0.01 times 400 squared. So that is going to be equal to 2 times 400, so 800 joules. The volume of water is 8 meters cubed. So our change in temperature is going to be, well, we need that much over that much to change 1 kilogram. Oh wow, okay, so we've got that meter cubed. So our we need the number of kilograms. So 1 kilogram needs that amount. So we're going to have to divide by 1,000 times 8 in order to get all of our temperature and mass thrown into all of this. So we can cancel. So we got 1 over 42000, since we got an 800 and an 8,000. So that is 100 over 42 times 10 to the minus 5, isn't it? Yeah, because I borrowed 2 at the top and there's 3 at the bottom. So that's going to be 2 and then 16 left. So, well, 2.4, give or take. Yeah, 16 over 42 is about 0.4, isn't it? So 2.4 times 10 to the minus 5. So yeah, A. Excellent. Yeah. When using Einstein's formula equals mc squared, a student enters the mass m in grams. If he uses a value of that for c, the speed of light, what are the units of energy? So we've got E equals mc squared. So C's gone in fine. He's put in mass in grams. So grams is kilograms, so we'll end up getting millijoules out on the other side. So it's going to end up being A. Right, so most of those were pretty quick, but we just had the 2 where we had to do a bit of calculation. So, well, 3 of them actually. You've got the one with a bullet, where you've got to do a little bit of pen and paper arithmetic. The same thing on question 9. There was another one as well, wasn't there? Oh, maybe there weren't. It was just really those 2, and the other ones were really quick sums. So yeah, those 2 where you have to play around a little bit. If you're not allowed to use a calculator, then doing this, getting these top-heavy fractions, is it does make things a lot easier. Because you can just drop these things out and say, okay, that is 2. I know I sort of glossed over it, but that's 2 over 2 and 16 42s. 16 over 42 is then 8 over 21. So you're looking at around about, well, you've got about 8/5 of these things. So yeah, 8/5 is about 0.4. So that's the power of top-heavy fractions. So just borrow some of your 10s, stick it all into your standard form, get a top-heavy fraction, and then work through it that way. And start thinking, that is around about 4 over 10, give or take, isn't it? It's about 4/10, which is why we're getting that. Okay, it's a little bit less than that, but it's still close enough. It'd be 2.3 something. But yeah, it's good enough for these 2 significant figure answers. But yeah, another quick bunch. So next we'll have the longer physics questions, and then the last video will be on the really long physics questions. So still 2 more videos to go.